it over to Mark Chidwick from Kanas Shelter Corp and E-Decisions to talk about your Innovation Fund project.
Very good. No, thanks, Alex. Oh, let's just title slide. Yeah, just jump to the next slide. Okay, our project is looking at a downtown office tower that we are converting from an office tower to a high-density residential affordable housing. And we were looking to then retrofit the heating and power that was built for an office tower. And of course, that's inappropriate for a residential building. So we are going to be implementing a microgrid, including some form of a combined heat and power, some electricity storage, and a variable refrigerant flow for heating and cooling. Okay, next slide. So when I've gone through these kinds of projects in the past, there's always 7 challenges that the developer goes through. The biggest one is the size. These on-site generators are often quite large, and it's challenging to find the physical space for these generators. The second 2 challenges, capacity and redundancy, are really tied together. Really what we would like to do is implement several on-site generators so that we can have some redundancy. But of course, if these are large, it's going to be very difficult to do that. We found that the generators have been evolving from 30 to 35% efficiency. They're now well over 45% efficiency. But what comes along with that is the capital costs for these newer technologies are higher. Well, the good news is that some of these technologies, the maintenance costs are actually going down. One of the bigger concerns, especially for high-density residential, is noise and vibrations. You don't want to have tenants complaining that they're sitting on top of a large reciprocating engine and they're getting shaken out of their apartment. Okay, next slide. So our objectives in this project are we want to reduce the cost for heat and power for the tenants. This is affordable housing after all. We want to reduce our CO2 emissions, but we also want to build a living lab so that we can demonstrate the efficacy of these modern technologies. So really the challenge that we're addressing here is as on-site generation technologies are evolving, what form of combined heat and power is more effective? Okay, next slide. And in this slide, we're looking at the evolution of combined heat and power systems. So we all understand the old style reciprocating engine. It's very mature, well understood, uses natural gas, but suffers from high maintenance costs, lower efficiency, and they're very, very large and noisy. But they're relatively cheap, $2,000 a kilowatt. I say relatively, it's depending on who you are. The next generation of combined heat and power is using fuel cells. Fuel cells have been around since the 1960s when they were used in the Apollo space missions. They're in their 4th generation now, very mature. However, they are very large, about a sea can size. They do increase efficiency, they're very quiet, and the nice thing is they have nearly 0 emissions, but they are twice the cost. Right, and I'll get into a little bit of this discussion in the next slides. The next generation that we see are linear generators. These are relatively new. They're in their 1st generation. There's really only 3 manufacturers around the world that we found, but they can be very small. That addresses the #1 concern for developers. Very quiet operations, higher efficiency, and the cost is somewhere between the cost of a reciprocating engine and a fuel cell. On the slide, it says $2,000. I think it's more like $3,000 a kilowatt. Okay, next slide. So we took a look at the fuel cells. Now, there's a variety of different types of fuel cells. I've listed four here: phosphoric acid, molten carbonate, solid oxide, and the proton exchange membrane. Um, each of these has pros and cons, but the one at the top, the phosphoric acid, is really the only one that would work for a on-site generation in a residential setting. And the reason being is that this is the only fuel cell that can follow the load of the building. So it will ramp itself up and down. Um, and it is relatively cold. 120 C we can deal with that. But for a solid oxide fuel cell at 1200 C, that's going to be very, very difficult to deal with in a residential setting. Okay, next slide. So we moved on to looking at linear generators. Now, the advantages here are they are much, much smaller than reciprocating engines of fuel cells, somewhere between 30 and 50% of the physical size, which means that we can implement several of them to provide redundancy. They also have smaller capacity. In the example that we found, there's a 200 kilowatt unit. And so if we were to implement 2 or 3 of those for the building, then we get the redundancy that we need to address our demand charges. They're actually quite a bit more efficient, ranging 45 to 50% electrical efficiency. I said the capital cost, I did say there, it's about the same as a reciprocating engine. I think they are somewhere in between a recip and a fuel cell, around $3,000 a kilowatt. But the good news is much lower maintenance, because the way these things work is the picture there. Sorry, I'm moving my mouse, so you can't see my mouse. But on both ends, you have a piston, and that piston is activated by heat that pushes the piston through a series of coils and magnets that creates the electricity. It gets to the other side, and the other piston pushes it back, and it goes just back and forth. These things run on air bearings, and so it's very quiet, very few moving parts, and doesn't have much in the way of maintenance costs. The maintenance costs on these are less than half of the cost of maintaining a reciprocating engine. And because there's very few moving parts, it's very quiet. Okay, next slide. So this sort of summarizes the challenges and the pros and the cons for the linear generator versus the fuel cell. So the cost, again, the slide is a little bit old here, but the cost is about $3,500 or $3,000 a kilowatt for the linear generator, compared to $4,000 a kilowatt for a fuel cell. The size is much smaller. There's one that we found that was about 8 by 8 by 3, compared to a fuel cell, which is a C-can size. The capacity on a linear generator can be as low as 200 kilowatts. So you could implement, say, 3 or 4 of them to meet your load, whereas the fuel cell runs at 460 kilowatts kind of flat out. The con of the linear generator is it's in its first generation, so it's unproven, whereas in the fuel cell, it's a 4th generation, so it's been well established. The efficiency of a linear generator is quite a bit higher than a fuel cell. The carbon capture is a little bit more difficult with a linear generator. It would require some post-combustion capture, whereas a fuel cell sort of has that built in. But then it doesn't increase the size of the unit, which is making things worse. We find that the maintenance cost on a linear generator, it ranges around 1 cent a kilowatt hour, which is less than half the cost of a fuel cell or a reciprocating engine. And funny enough, a con for the linear generator is they are manufactured in the United States, and depending on your political views, we'll see whether that's a pro or a con. Whereas the fuel cell, they're manufactured in Korea. They're really very popular in Korea and Asia. So they've got quite an install base. Next slide. So this is what we are modeling for the office tower, or the conversion project downtown. We're looking at implementing two 200 kilowatt generators. You can see the top chart is the electricity consumption that we anticipate for the building. The second line chart is the heat consumption for the building. And so the little gas gauges over to the right show me how much electricity, heat, and cooling the building is going to be demanding. So we can see here the red bars at the bottom show the electricity, heat, and cooling that this system will not provide. So looking at the gas gauge, we can see it's 100% of the electricity demand we will supply. Nearly 100% of the thermal demand will be supplied. And then if we
So where did you put the barrel in?
sorry, I wasn't sure if there was a question there. Okay, so if we look at the economics, I'm assuming $5 a gigajoule for natural gas, and we measured out the capital costs, the lifetime savings, the simple payback, net present value, and the emissions reduction.
And go to the bottle depot tomorrow first.
So the
Go to them tomorrow.
the financial metrics on this look actually very good. However, the emissions reduction is only 16% towards our net zero goal. But because, excuse me, because the financials are so positive, we can afford to look at using renewable natural gas at 3 times the cost, $15 a gigajoule. So now the simple payback goes up, the net present value goes down, but the emissions reduction is very, very attractive. So normally when you introduce renewable natural gas into a project, it kills the financials. But because the financials in this project are so good, the project can withstand this. Okay, and the final slide. So we see this type of technology being useful in owner-operated buildings, and that means the facilities where the owner of the building is also responsible for the energy costs. So things like post-secondary institutions, grocery stores, high-density residential, and so on. And also for buildings where you cannot tolerate heat and power outages. Grocery stores is a great example of when we had the floods back in 2013, and in High River, the inventory they lost was just terrible. And also facilities interested in emissions reduction. I know our post-secondary schools are all over this. Yeah, and I think that is what I have today.